Welcome to our lecture on DC microgrid and control system. Today we shall discuss about modeling of the solar photovoltaic cell as well as the solar element together. So, this will be more physics. Photovoltaic systems, they are at a p-n junction diode. Now, thereafter generic photovoltaic cells, and thereafter we shall discuss about simplest equivalent PV cell circuit and more accurate PV cells equivalent and the MPPT control of the solar photovoltaic. As you know that it is needless to say that photovoltaic is a conversion of the light directly into the electricity through the semiconductor material. The basic component of a PV system is a solar cell. If light with the adequate energy falls into the silicon arranged to form a p-n junction and penetrate to a point near to the junction, then because of the photoelectric effect it will create free electron near the junction. This electron immediately move under the influence of the p-n junction electric field. It is quite, you are familiar with this phenomena. This electron can be collected by the metallic grid and the electric current will flow if the grid is connected to the metal contact or on the other side of the cell by the external circuit. So, essentially this is called cell. Ultimately you have a combination of the cell, that is called the module, and ultimately these are the parallel module that makes it an array. So, the PV hierarchy system are shown in the figure 1. One solar cell has output and around a diode, that is 0.5 to 0.6 volt. Very few application works at this voltage. So, solar cells are connected in series in a module to increase the output of the voltage of the module. The number of cells in a diode, the number of the cells in a module is governed by the voltage of the module. Photovoltaic modules, manufacturers make modules such as it works at 12 volt batteries. Depending on that different kind of setup, you can have a different voltage, you can have a 35 volt or 38 volt MPPT voltage, making them into the form of array. So, allowing some of the over voltage to charge the battery and to compensate for the output under non-standard state condition, that is actually the we generally prefer 27 or 25 degrees centigrade, 0 degree centigrade and the 1000 watt per meter square radiations. Modules usually have 30 to 36 solar cells in series to ensure reliable operation. To increase the module output current, the series strings of the solar cells are connected in parallel. Based on the desired current and the voltage output of the module, solar cells are connected in both series and parallel combinations. The modules can then in turn be connected in series or parallel to have the desired PV voltage and current. Such combinations of modules are referred as arrays. So, that is called array. Now, let us come to the p-n junction diode. So, it is quite familiar, I have nothing to be discussed much. Consider the conventional p-n junction diode, the characteristics of which is represented in figure 2. If a voltage Vd across the diode terminal is applied, forward current flows easily through the diode from the p side to the n side, but if tried to send a current in the reverse direction very small, that is 10 to the power minus 12 ampere per centimeter square, reverse saturation current I0 will flow. The reverse saturation current is the result of the terminally generated carriers with the hole being swept into the p side and the electron into the n side, quite familiar the diode bridge phenomena. So, and the forward junction and the forward direction, the voltage drop across these diodes is only few tenths of the volt, that is around 0.7 volt or 0.6 volt for the silicon. This is the p-n junction diode, this is a symbol of the p-n junction diode, this is I V characteristics of the diode, and that is I D equal to I 0 is the reverse saturation current e to the power, this will be the Boltzmann constant, and another constant comes into the picture V d minus 1, and this will make it a p-n junction diode. Now, you can see that the voltage and the current characteristic of the p-n junction diode is described by the following Shockley diode equation, that is I d equal to I 0 e to the power q V d k t, where k is a Boltzmann constant, t is the temperature in Kelvin, and minus 1. So, that is the I d is the diode current, V d is the voltage across the diode terminal, I 0 is the reverse saturation current, q is the charge of the electron, k is a Boltzmann constant, and t is a absolute temperature. And let us assume that p-n junction is exposed to the sunlight. As photon absorbs, whole electron pairs are formed. So, this will be photon, actually what happened, then there will be a electron in the conduction band and holes will be there in the valence band. If this mobile charge carrier reach the vicinity of the junction, the electric field in the depletion region will push the hole into the p side and push the electron in the n side. This is the actually the layer, this is the n type and this is a p type, ultimately they will change over, and thus what happen, p side accumulate holes and the n side accumulate electrons, which creates a voltage, and that can be used to drive the current to the load. That is the principal operation of this p-n junction diode. When photons created, the holes electron pairs near to the junction, the electric field in the depletion region sweeps hole into the p side and sweeps electron into the n side of the cells. Now, if electrical contacts are attached at the top and the bottom of the shell, electron will flow out from the n side into the connecting wire through the load and back to the p side as shown. The electron moves around the circuit when they reach to the p side and they combine with the holes completing the circuit. So, that is something like the battery. By convention, positive charge, positive current flow the direction opposite to the electron flow, and the arrow in the figure 4, this is the current, shows that current going from the p side to the load to the back to the n side. So, this is the electron flow from the n side to the load and back to the p side, where they recombine with the holes. Conventional current I is in the positive direction. Now, let us make an equivalent circuit of it. The simplest equivalent circuit is the PV cell and the load, and that can be think of as a a current source and a diode parallel to it and the load. So, simplest equivalent circuits of the model for a photovoltaic cells consist of a real diode in parallel with the ideal current source as shown in the figure 5. The diode current source delivers the current in proportion to the solar flux to which it is exposed, where there are two conditions of particular interest for the actual PV and for its equivalent circuit as presented in the figure 6. These are short circuit current and the open circuit voltage, we will see later. But there is a problem of short circuiting a current source, but those kind of problem will not be here fortunately. When the leads to the equivalent circuits for the PV cells are shorted together, no current flows in the real diode since Vd equal to 0. So, all the current from the ideal source flows through the shorted leads. Since the short circuit current must equal to ISC, the magnitude of the ideal current source itself must be equal to the ISC. And similarly, voltage and current equation of this equivalent circuit of the PV cell are shown in the figure 6b, and where I equal to ISC minus ID. So, this is basically the open circuit and this is basically the short circuit. Now, considering this equation, and we know that actually the subtracting this equation I equal to ISC minus I0, this is essentially the ID. So, I0 e to the power q k T V t minus 1, and observing this equation and the equation 2, we can observe that ISC is added to a diode curve of the figure 2c. So, this is the curve, and the current voltage relationship for a PV cell when it is dark and the light based on 2 is depicted in the figure 7. This is the dark condition and current will go back, and this is the light condition where ISC will be positive, and this is the case. And when the leads from the PV cells are left open, that is I equal to I0. So, this open circuit voltage will be V0C equal to KT by Q ln ISC by I0 plus 1, and thus you can calculate the open circuit voltage in the lighting case. An equivalent circuit, circuit when series resistance is included as shown in the figure 8. This is the figure 8. So, ultimately you will have a resistance here, thereafter a load. This PV mathematical equation with its circuits can be analyzed by I equal to ISC minus ID equal to ISC minus I0 e to the power this one, where the impact of RS is added. So, that is basically the intrinsic resistance. So, Vd equal to V plus I into RS, and the substituting you get this results, and thus what happened, the general equivalent circuits with the series and the parallel resistance combinations is illustrated in the figure 9. So, this will be the figure overall, this is Vd, and ultimately there will be a resistance parallel to the diode, and overall circuit will be looking like this, and thus you can write I equal to ISC minus I0, this is the exponential, thereafter the drop due to this part of the it for the more complex equivalent circuit. Now, while analyzing it, so you can choose a different kind of equivalent circuit for suitable for taking your model, and instead of the taking actually this MATLAB Simulink model, you can make your own model if you know these values, and it is not difficult to find it out their values. Circuits for the PV cell includes both parallel and the series resistance. So, now we require to track the MPPT voltage. The MPPT system, PV solar MPPT, we have seen the wind MPPT, now it is a solar MPPT system, adjusts the duty cycle of the converter in such a way that operating voltage of the panel is consistently maintained at its maximum operating point. Maximum operating point generally changes due to the temperature and irradiation. Mathematically, this process can be evaluated by modeling the various components of the solar system. The mathematical model establishes the theoretical relationship between the duty cycle and various parameters of the PV system, that help us designing the algorithms and that enables the maximum power transfer. So, you have a DC to DC converter. The most PV application boost or the buck DC to DC converter are used for MPPT control. A boost converter is a commonly used circuit to step up the voltage from the DC source, while a buck converter is often used to step down the voltage. So, for this reason you have a DC to DC converter in between, and that will feed the load, and generally it will be maintained at the MPPT voltage. In order to ensure the maximum, it is called a reverse converter because you wanted to fix up the input voltage and your output voltage will be remain constant. In order to ensure the maximization of the power extracted from the PV source, the interface power converter must be capable of self adjusting its own parameter at runtime, thus changing its input voltage current level based on the PV source of the MPPT position. Suppose that the DC to DC converter is a dynamical optimizer and that the control parameter is duty cycle of D, the main switch is shown in the figure 10. Then what happened? The connection schemes of DC to DC converter dedicated to the dynamical optimization of the PV generator. Assume that the DC to DC voltage conversion ratio of the converter is D equal to V 0 by V I in case of the buck converter for the continuous mode of conduction. The equivalent resistance and the voltage seen by the PV source terminal can be expressed by, that is basically depends on its duty ratio. So, that will be actually R load into D square, and where D is less than 1, thus you have a effective more resistance, and similarly V in equal to V 0 by D. The duty ratio, the duty cycle value D must be changed continuously by a controller to ensure that the PV generator always operate at its MPPT for whenever the irradiation and the temperature and other operating conditions. Based on the instantaneous values of the current and the voltage sensed at the PV generator terminals, the MPPT controllers dynamically adjust the converter's duty cycle to follow the MPPT as shown in the figure 11 that I will show in this figure. So, you have a solar panel, you have a current sensor, you have voltage sensors, and it will try to have a different kind of algorithm are there for, namely perturb and observe. You have a transconductance method, and that will be a digital implementation, and it will drive this DC to DC converter, and ultimately it will track the maximum voltage. So, the MPPT controller can be realized based on different methods and algorithms. Most popular methods are known as, or it is well established, or PO method, that is called perturbed and observed, and the incremental conductance or INC. The practical implementation of MPPT controller is mostly digital. In a digital domain, we will have to have a nowadays microcontroller. Simple microcontroller can do that job. Otherwise, you can have also a complex FPGA and all those things, you can also use that. So, perturbed and observed methods are the most popular algorithm belonging to the class of the direct MPPT technique, and its characteristics by the injections of the small perturbations into the system, whose effect is used to drive the operating point. So, it is, if you generally change it, if you see that power is increasing, you go on that direction, it will continue to that direction, the multiplication of the voltage and current gives you the more power. Otherwise, you will actually track reverse. So, the PV operating point is perturbed periodically by changing the voltage at the PV sources terminal, and after each perturbation control algorithm compares the values of the power fed by the PV sources before and after the perturbation. If after the perturbation PV power has increased, the operating point has been moved forward the MPP. Consequently and subsequently, the bottom imposed to the voltage will have the same sign as that of the previous one. Now, if after a voltage perturbation the power drawn from the PV array decreases, this means that the operating point has been moved away from the MPP. Therefore, the sign of the subsequent voltage perturbation is reversed. The switching converter is used to drive the perturbation of the operating voltage of the PV generator. Students can refer to this flowchart of the perturbed and observed on conductance method. It is well available and well documented literatures. So, two basic PO configurations can be adopted for controlling switching converter and realizing the PV source of the perturb. Present will be figure 12 next, and first one involves direct perturbation of the duty ratio of the power converter. So, this is basically basic scheme. Perturbed and observed, this is the what we do actually, we sense the voltage and current, and this is a perturbed and observed method, and we feed the PWM. And also not only that, some controller require also the voltage control. Not only that, the duty cycle is coming out by the maximum power, we require to have voltage control, both required to incorporate, and ultimately this one is most preferred, because you require to charge the battery as 12 volt. So, you require to track the MPPT as well as you require to charge the battery as a 12 volt, and for this reason the second method is preferred with PO. So, in the second one, the perturbation is applied to the reference voltage of an error signal that generates the signal controlling the duty cycle. In the first case, converter operates in the open loop, that is a problem. So, you do not have any information whether this you require to leave this voltage at the desired level, and by tracking the MPPT whether you are maintaining that. So, the converter operates at the open loop after each duty cycle perturbation, while in the second case the converter is equipped with a feedback voltage loop, and thus this method is preferred. Thank you for your attention. I shall continue with the discuss with the modeling of the different entities of the DC to DC converters. Thereafter, we have designed this actually wind turbine, that we have designed the solar cells and solar panel, and these are the different entities of the DC microgrid. Thank you for your attention. So, thank you.